Okay, so let's work this problem. This will be the first problem we work where we'll use the Mueller-Breslau principle to help us draw the influence line to get started. So we have two things. I think, just one thing. We want the maximum positive moment that can be developed here at point D in the beam. So what I'm going to do is use Mueller-Breslau. So I'm going to draw a kind of template, and I'll extend down some key points. So there's the end, there's point D, there's a reaction, there's a hinge. So if I want the moment at D, there's D, what do I have to assume in Mueller-Breslau? I come to D and I assume that there's a what? A hinge. Right? And then I also assume that I'll have positive bending moment on both sides. Now when I do that, how do you think point B is going to move? Up or down? Up. Up. So I'm just going to assume some up position and then see how that's going to affect things. So on the right hand side, it'll be fixed at E. It'll have to go up. As I push D up, it'll seesaw over C and go down to B, and the hinge at B allows it to bend back up and connect at A. So there's the shape of my influence line. So I need to establish a value here. For example, if I can get this high value, then similar triangles, it should tell me this one. In fact, if you look at those two triangles, they both have a dimension of 5. So if I can find this value, then I know this value automatically is just negative. So I'm going to find this one. So I'm going to redraw my structure, and we'll talk about where that goes. So I've got my pin at A, and then I have a hinge at B. I've got a roller at C. Then D. Well, D's not a pin anymore. That was just my Mueller-Breslau kind of virtual connector. So it runs all the way out here to another pin at E. So if I want this value right here, that's at position 15 feet over, I'm going to do the same thing here. I'm going to put it right there. So there's my unit value that I had previously that we used in our tabular method or in the function method. In both cases, we would use our load. So there's the position. So that position corresponds to this value on the influence line. I did leave something off here. I forgot to put my value. This is the moment at D. So I'm trying to find the moment here for that position. So how best do you think I should do that? Well, probably I'll draw a free body diagram of this left side, right? If I can find this reaction, then I can cut it and find the internal moment. So I'm going to redraw this. Let's see. I'll draw two free bodies. I'm just going to break it apart at the real hinge just to show you what we're doing. So I would have a reaction at A. Now when I pull this hinge apart, I would actually have shear there. That would be the shear at B. And of course, equal and opposite would be the shear at B on the other side. Then I would have my reaction at C, and then my reaction at EY. So that's the same structure. I've just broken it apart here at the hinge. And remember that my unit load is still here. So let's just put some dimensions on this. So this is 5, 5, 5, 10. Right? I couldn't solve this with one free body because I've got two unknowns, then 1 and 1. That's 4 unknowns. So I break it apart here, right? And now I can solve it. So let's look at this side right here. What's AY equal to? What's the shear equal to? 0. There's no load there, right? So that means there's no reaction. There's no shear. So if the shear is equal to 0 here, then it's equal to 0 here. Right? So now now I have a free body with just two unknowns. I want to find EY. What do I sum moments about?
C.
Yeah, so I'll assume right-hand rule, and I will sum moments at C, make sure I'm in equilibrium. So when I do that, my unit load creates what kind of moment about C? Negative. So it'll be -1, has a moment arm of 5. My EY reaction creates positive moment. The force is EY, and the moment arm is 15. So it looks like EY is going to be equal to 1/3. So now I'll cut the structure from D to E. I will put my EY reaction on that I just found, which is 1/3, and I'll look for the moment internally at D. So this first set of free bodies, free body diagram 1, free body diagram 2, that was to find my reactions. Now I'm writing a third free body diagram to find the moment. So I can find the moment by summing the moments at the cut. Make sure it's equal to 0. With right-hand rule, the moment at D is positive or negative? Negative. And the 1/3 is going to create positive moment. So that'll be 1/3 times the distance of 10. So it looks like the moment at D is equal to, oh, that's positive, is equal to 10/3. And it'll be 10/3 feet. So this becomes 10/3. So similar triangles tells me this value here is negative 10/3. And don't forget this all the values here. The ordinate has a value of feet. And we don't care about the abscissa because it's hard to say. We don't like it. So there it is. A little bit longer, but still less effort than doing the equation method where you'd have to write 1, 2, 3 different equations. You'd still be in the first one probably drawing free body diagrams. So now we answer the problem. So here's my here's my influence line for the moment at D. It says what's the maximum positive moment that can be developed at D for a concentrated load of 4 kips, a uniform live load of 300 pounds per foot, and a dead load. So let's do the concentrated load first. It's a live load, so it's live. What's the value of the concentrated load? 4 kips. Now, so where do I put it to create the maximum positive value? Well, here's the maximum positive ordinate. That's probably where I will put it. If I wanted the maximum negative moment, where would I put it? Here, over the maximum negative value. So I'm going to figure this out by saying 4 kips times my 10/3 feet will give me 40/3, which is 13.33. And that'll be kip feet. So there's the positive moment created at D when the concentrated force is actually at B. Let's do the live. Let's do all of our live pieces first. So the next one will be the uniform load. What's the value of the uniform load? The live uniform load. Yeah, it's 300. I'll just make that 0.3 kips to keep everything in kips. How about that? Now, where do I put my load? Where do I start it and stop it? And of course, I could start it and stop it multiple times. But where would I put it so that I create the most positive moment? Would I do it from 0 to 10? No, because that's going to produce negative influence. So I'll do it from 10 to all the way out here to the end. So I'll need to find the area of this positive part of the curve. So I'll start with the intensity of the load, 0.3 kips per foot. And then this is a triangle. What's the area of a triangle?
1/2 base times 10.
Yeah, so 1/2, the base. What's the base? 15 feet. What's the height? 10/3 feet. So your units come to kip feet. I don't know what that is. That's a mess. $7.5? I'm guessing. That's wrong. 7.25.
No, 2.2.
What is it?
Oh, I forgot the 10 there. It's not all.
7.5.
7.5? Anybody else get 7.5? Anybody
Yeah, I got
trying?
I got that.
Oh, good. One person. Good.
7.5.
Very good. I like it. And now we'll do the dead load. In this case, it's a uniform load. Now, do we control where the dead load is applied? No. It's going to be applied across the whole structure. So it is possible, depending on the shape of the influence line, even though you're looking for the positive value, when the dead load's applied, it could give you a negative value. It's kind of a constant for the problem. It's just fixed. So the dead load for us is 200 pounds, or 0.2 kips per foot. And then I've got a negative triangle and a positive triangle. So they'll both have that 1/2 base times height. So I'll pull the 1/2 out. So the base of the first triangle is 10 feet. The height is negative 10/3 feet. The second triangle has a base of 15 feet and a height of positive 10/3.
I got
1.67.
I got 1.67.
That's what I got. I did my Rain Man. Only on Tuesday. Oh, it's Thursday. Shoot. So what's the total moment? The moment at D would be the sum of these things. So that plus that is 15, plus that is 22.5. Is that right? So the maximum positive moment is 22.5 kip. What if I was looking for the maximum negative moment? What would change? Would this value change?
No.
No, the dead load would not change, but this value would change. I would find the area under this part of the curve to give me a negative value, and I'd also move my point load to also be over the point. So a different loading scenario. Now really, if you were an engineer, you would really care what's the maximum moment. You'd look for the positive moment, you'd look for the negative moment. If you were doing reinforced concrete, you'd have to worry about both of them, because this is a moving load, right? So at some position, it's going to create a big negative moment at D, and some other position is going to create a big positive moment at D. You'd have to have reinforcement for both of those. So let me redraw the structure here real quick. And I'll sketch on the position of the loading just so you can see it. So there's the original structure. So the dead load extends over the whole structure. The uniform live load only goes from where? From C to the end. So there's the live uniform load. This is the dead load. And then where does my concentrated load go? Right over D, which is right here. So that would be where the 4 kip goes. There's the live uniform load. There's the dead uniform load. So that loading pattern creates this positive moment. A different loading pattern would create the negative moment. You'd see the live load switch to this section, right? And you'd see the concentrated load switch over to be the mid-span here. Let's get a different value. Any questions about that?
No.
Is this a likely exam 2 problem?
Yes.
Yes. Would it be this problem? No. Well, maybe. I like that. Possibly. It is not, up there with winning the lottery.